Hi, welcome to the third part of the lecture entitled Mass as Triple Integrals in Rectangular Coordinates. So before we have been evaluating triple integrals over rectangular boxes. So now the question here is what if the solid is not a rectangular box, no? So what if it's an irregular, oops, sorry. What if it's an irregular solid? So the theoretical way of doing this is to enclose that irregular solid with a box, okay, and define a new density function. And the density function will just be the same density function if the point is on the original solid, and if it's outside the original solid, we just set it to 0. And then we have this neat theorem here that says that the mass of the original solid will be the same as the mass of the rectangular box, given that the density is equal to this. Okay? So, but this is practically useless. No, this is just a theoretical way to define the triple integral over irregular solids. So, in general, it is very hard to compute the mass of an irregular solid. So, we have to assume that the solid has some properties that could be exploited. So, to evaluate triple integrals over general solids, what we can do is to classify them if they have this property, no, the property is being of type xy, type xz, type yz, and this is reminiscent of what we've done, no, classifying regions as type 1 and type 2. Remember, a type 1 region has vertical boundaries, whereas a type 2 region has horizontal boundaries. So we might as well have the same concept of classification of solids. So what really is a solid of type XY? So a solid of type XY is such that, okay, at you have a projection R on the XY plane. No? So this is your projection R on the XY plane, and at each point XY on this projection, no, you can define the floor and the roof of the solid in terms of a single function, no? So for instance, at this point xy, then the floor is defined by g of xy, and the ceiling is defined as g2 of xy. So this is g1 of xy, and this is g2 of xy. So that is the solid of type xy. So again, you have a projection R, no? So it's a projection R, and then the solid is now bounded below and above by two surfaces defined by, say, G1 and G2. Okay? So how do you evaluate the triple integral of a solid of type xy? So it's very easy. So what you do is that you exploit that there is a single projection onto the xy plane. Okay? So because there's a single projection onto the xy plane, so you can think of dividing this into a single and a double integral. Okay? So the innermost integral will just be an integral over over the elevation dimension of the solid. So that means that this is in terms of z. So that's why you have dz here. And over all xy in R, the lower and upper limits of integration are g1 and g2. Okay, and you still have the same integrand. Okay, so dv will become dz dA. Okay, so after evaluating this with respect to z, then you will get a function in terms of xy, and therefore this double integral is well defined because this is over the projection of the solid onto the xy plane. Okay, so again here, so you have a projection onto the xy plane, and at each point on the xy plane, you draw maybe a segment above that point, Then you have the limits of integration. The lower limit will be the surface that defines the floor of the solid, and the upper limit will be the surface that defines the roof of the solid. Okay? Let's have an example here. So let's evaluate the triple integral over g of 6xy dv, where g is the solid bounded by the planes x equals 0, and this is the yz plane, y equals 0, and this is the xz plane, and then you have x plus y plus z equals 1, and x plus y minus z equals 1. So how do you draw this x plus y plus z equals 1? So this is x plus y plus z equals 1, I think. No, so you just have the x-intercept would be 1, y-intercept would be 1, z-intercept would be 1, and you just draw the triangle. How about this plane here over here? So again, the x-intercept is 1, the y-intercept is 1, and the z-intercept is minus 1. So here, the triangular plane is this one. And then you're also bounded by the YZ plane. The YZ plane is this plane. It's the plane of the slide. And then y equals 0 is the XZ plane, which is this plane. Okay? So therefore, you have this solid. I hope you can see this. No? So you have like a pyramid on top of the XY plane, and you also have like a mirror effect. No? There's also a pyramid below the XY plane. So G is a type XY solid because you have a projection onto the XY plane, and the projection is nothing but this triangle over here. And then for each xy on the projection, you can well define the roof. The roof would be this one, the roof of the solid, and the floor of the solid. No, the floor of the solid. So G is a solid of type xy, and it's bounded below by this, no, this one. Z is equal to x plus y minus 1. It's also bounded above by z equals 1 minus x minus y. Okay, so again, you have to rewrite this as z equals a function of xy because that's how you do it here, right? This is the lower boundary, this is the upper boundary. And remember, R is the projection of G onto the xy plane. And that's why we say that it's a type xy because you have a projection onto the xy plane. So now let's evaluate. So the triple integral of 6xy over g dv will be a double integral of a single integral. No, the single integral will be the single integral of 6xy dz, and you evaluate z equals the lower limit and z equals 1 minus x minus y, which is your roof, no, yung ceiling function. Okay, so you can also go ahead and define the limits of integration of this double integral, and we have that already when we discussed the double integrals before. So this is the region, remember. So this is a type 1 region. That means that you can think of this as a region with horizontal boundaries. So that means that for any point x here, you have a floor and a ceiling as well. So y equals 0 is the lower limit, y equals 1 minus x, it's the upper limit, and then the x here ranges from 0 to 1. Okay? So now we have fully written the triple integral as an iterated triple integral. Okay? So you do the evaluation here. Let's try this step by step. So 6xy with respect to z. What is the integral? The integral of this? The integral of that is 6xyz, because this is a constant with respect to z. So this is the integral, and then you evaluate this over these limits of integration. And when you do that, you get this kind of nasty polynomial over here. And then you evaluate the integral over y again. So for instance, this one, the integral is 6xy squared. This one, the integral is 6x squared y squared. This one, the integral is 4xy cubed. And you evaluate this over y equals 0 and y equals 1 minus x. Do some simplification. Uh, you get this. So it's not, there are a lot of steps that are being that are being skipped here, okay? So after doing a lot of simplification, get something like this, and you do some substitution. It's not very hard to do. Let u equals 1 minus x, and then du equals minus dx. You can also just expand this, but let's just do the substitution, and when you do everything, you get 1 over 10 as the final answer. Okay? So solids of type xy again. You have another example over here. So let's evaluate triple integral of x dv. No, we're over g, where g is the solid in the first quadrant, bounded by, this is a plane. No, this is a plane, and this is a what is that? Y equals 4 minus x squared. This is a parabolic cylinder. This is actually a cylinder as well because you have a missing variable, no? And then y equals 0. So very important in how you evaluate triple integrals is the ability to draw three-dimensional objects. So now please review how to draw a plane, how to draw parabolic cylinders. So maybe not parabolic hyperboloids yung saddle, no? But you review how a paraboloid looks like. Okay. So for instance, y plus z equals 4, how do you draw that? So you think of this as a cylinder. So it's a cylinder because the x is absent. So on the yz plane, you draw the line y plus z equals 4. So it's nothing but this one. And then you just propagate it along the axis that is missing here. So it's the x-axis. So the plane is actually this plane. No? So this is y plus z equals 4, and then you propagate it along the x-axis. So this one is just the green surface. And what about y equals 4 minus x squared? Again, you treat this as a cylinder. So you look at the variables, you have y and x. So you look at the yx plane, xy plane, and you draw y equals 4 minus x squared on the xy plane, which is nothing but a parabola. No, parabola. Y equals 4 minus x squared. And then this is now your generator, and you propagate this along the axis of the missing variable, which is z. So really, the solid looks like this. No? Ganyan. I don't know. So because you're just looking in the you're restricting ourselves in the first quadrant, then you just get this solid. And let's verify that this is in fact a solid of type xy. It's because you have a projection over here. And then after determining the projection, you look at each point xy on the projection. So after if you get an arbitrary xy on the projection, can you define the roof and the floor of the solid? Yes. So the floor of the solid is nothing but z equals 0, which is the xy plane, and the roof of the solid is this plane over here, y plus z equals 4, which you can rewrite into z equals 4 minus y. So you have this as the floor function, and this is the ceiling function. And the projection G onto the xy plane is the parabola y equals 4 minus x squared. So again, so how do you evaluate? The triple integral can now be written as a single integral, and then you do the double integral, no? So dz, and then the floor function is equals 0, and then the ceiling function is equals 4 minus y. And then after looking at the three-dimensional object, you look at the two-dimensional object so that you know how to evaluate the double integral. So you can look at this as a type 1 region. So at any point xy, so you have the lower limit and the upper limit. The lower limit is y equals 0, the x-axis. The upper limit is y equals 4 minus x squared. And that's why you have these limits of integration over here. And the x ranges from 0 up to 2. That's why you have 0 to 2 over there. So once you have this part, this is the most important part in the setting up of the triple integrals. And after that part, it's easy peasy because you just have to do iterated integrals and integration. So after doing the innermost integral, you go with the next innermost integral and then the last integral so that you will get 32 over 3 as your final answer. Okay? The last part of our lesson will be to solve these exercises. Okay.